Okay. So we have the equivariance condition here. And I can now left multiply with the inverse of that matrix. Sum over j is the sum over neighbors. I could have an additional summation over channels here, which I'm not writing because otherwise this would become even more cluttered with indices. And this we can compare to the original equation, equation 32. And so here I have something with f out, comma I of type L on the left-hand side. We have this equation. And we have that one. And so from this, I get a new equality. Yeah? And so I'm writing, so what I obtain is that this part is the same as WLK. And I'm writing this one on the left-hand side. So comparing with equation 32 gives me that WLK so I'm making several changes now. The Rj minus Ri, I'm just going to abbreviate this as R. And I have multiplied from the left with the inverse of this matrix. So this is dl of g. And then I have WLK of R. And from the right-hand side, I still have, from the right-hand side, I multiply with the inverse of that. So dk minus 1 of g. And this is now a matrix. We can, in this matrix, we can vectorize. And now we're going to use a special transformation here, namely if I have the vectorization of a product of three matrices, the vectorization of matrices A times B times C, I can rewrite this as Kronecker product of C transpose times A times the vectorization of B. And this equality here, if you want to read about it, There is a lecture note or document by Xishang, by the way, one of the pioneers of probabilistic graphical models. And it is aptly called Kronecker product and vectorization. All right, so we have, this here is A, this here is B, and that is C. So here I have D, K, G to the -1 transposed. But for SO3, the Wigner matrices are orthogonal, so the transpose of the inverse matrix is just the original matrix. I can just write dk of G. And then Kronecker product times here matrix A. So dl of G. And the whole thing multiplied with the vectorization of WLK of R. Okay, now this here I wrote, or here I called it Kronecker product, but this is exactly the tensor product that Peter talked about last time. And this tensor product, okay, we'll need a new board. This tensor product is gives me a reducible representation. So I had dk of G, tensor product dl of G. This is going to be a matrix which is densely occupied. So the tensor product of representations is again a representation, but a reducible one. And now we can use a change of basis where I transform into a space corresponding to the direct sum of irreps. Yeah, so here now I have a direct sum. With angular momentum going from absolute value of k minus L to k plus L. Okay, so what we have here, this is a direct sum of irreps in our case of SO3. And these here are the Clebsch-Gordon coefficients. And here together they implement a change of basis. And this equality here is also called the Clebsch-Gordon decomposition. In this decomposition, we're now going to use in that equation that we had over there. And I multiply, yes? Okay, yeah, so the vectorization is just rewriting the matrix as a vector. That's all, yeah. Mm-hmm. Reshaping, flattening, yes. Good. So we use this, and we multiply from the left. I multiply from the left with the inverse of that matrix. So the Clebsch-Gordon matrices in general, they're unitary, but in the case of SO3, they are also normal. And so I can write that QLK times the vectorization of WLK so we've isolated now by left multiplying with QLK. We have now isolated this direct sum here. And as Peter pointed out, this matrix here is block diagonal. Yeah, so it's the representation here is a lot sparser than that one. And because it is block diagonal, so we have zeros here and zeros there. If you think what happens if we apply to a vector or a matrix, we have zeros here and zeros there, so we can isolate subparts. We can isolate subvectors. And this will ease notation a little bit by concentrating only on the jth subvector in the next few lines. So I'm going to, I'm going to pretty much copy that equation, except instead of the direct sum, I'm only looking at the jth part. Here I'm writing subscript capital J for the jth subvector. And now I'm only taking here the corresponding part of the block diagonal matrix and multiplying with the suitable subvector on the right-hand side. All right, so this we got from the equivariance requirement, and this we can compare to how spherical harmonics transform. So we're going to identify this with spherical harmonic of type J evaluated at location R. And this I now, well, this is how spherical harmonics are rotated. Yeah? This is what I assume known. And by comparing these two So this is the rotation behavior. And by comparing these two equations, we see that we can compose our filter in terms of spherical harmonics. So I'm multiplying here from the y is this, and so the vectorization so I'm using this equation and multiplying from the left with the inverse of QLK. And then I get and here we were only looking at the jth subvector. So now I revert to using all components. So I don't have a subscript j here. Now I'm using all components. So if we choose WLK like so, we obtain a filter that does satisfy this equivariance condition from which we set out. And now so far we have only been modeling angular behavior, and this derivation also goes through if we multiply this angular part with any radial part, in particular a learned radial part. So multiplying with a scalar means we do not change the type of our filter, and so what we can do here is multiply with some radial function phi that depends only on the length of a vector. And so overall what we get is the following. So summation over small j is the summation over the neighbors. These here were my type K input features. And the filter we used looks like, or the filter that we can use looks as follows. Here we always had the vectorized version, so now I am unvectorizing. I'm turning my vector back into a matrix. This is the radial part, the one where we can finally put in weights, where we can learn something, because the rest is just fixed. Yeah, in the remainder of this filter, our only hyperparameter is up to what order of angular momentum we're going. Okay, and if we want to look at dimensions a little bit, okay, anyway, let's put this merits a frame. This is, so some variation of this you will see in most papers on SO3 equivariant message passing neural networks. We have tensorial features associated with atoms, and these we weight with a steerable filter, and the steerable filter is constructed by taking spherical harmonics up to some maximum order, which you specify with some learned radial modulation. And we have the Clebsch-Gordon coefficients that some authors call it symmetrize this product, so that makes sure that they transform correctly under rotation. And if we do take tensor products, we might, there are different pathways. So when we take a tensor product, we always obtain a range of angular momenta, and sometimes we create entities with the same, so by combining different filters with different features, we might get entities with the same angular momentum. And one way to inject weights is by weighing these different paths. And the other way of injecting parameters or a place to learn is by well, using some neural network here. Yeah? So this will be some MLP, let's say. Then altogether, this was a linear filtering. And in such networks, we also need a non-linearity, of course. And there are two ways of introducing non-linearities. One is to use a, so here we get messages, and one way is to take these messages to some order. So these are called, in the language of the maze orders, high body order interactions. So qualitatively, what happens is that if we have some function of node, let's say some function that depends on neighboring atom 1, and we have some function that depends on neighboring atom 2, and some function that depends on neighboring atom 3. If we now take the square of this, then I obtain these terms which are then bilinear in the contribution of different atoms. And if I take a third power here, I get even higher polynomials. So this is one way of introducing nonlinearity, and this is what Mays from the Chani group does. And another more typical way is to introduce gated nonlinearities. This was first proposed by Maurice Weiler, who was a physics student in Heidelberg. And in gated nonlinearities, we use these incoming tensorial messages to produce scalars, which are then sent through some nonlinearity and are then multiplied with the tensors themselves. I don't want to go into detail now because it's not so important here, but these are the main ways of introducing the nonlinearities which we need to come up with a nonlinear neural network in the first place. Okay. Do you have questions here? So if somebody has a computer with a HDMI port, then we could show pretty pictures if you open the OneNote document. But if not, I can try and explain a little bit or summarize a little bit in words what's happening. So both the Wigner matrices and the spherical harmonics, they both offer a description. So both are representations of SO3. And there's an isomorphism between the two. And the difference is that the spherical harmonics, they span a function space. And these Wigner D matrices, they give us a vector space. And if we take the function space perspective, what spherical harmonics do is that, just like we know from Fourier series in one dimension, that they allow giving us, as we increase the angular momentum, they give us more and more faithful representations of functions living on the sphere. So in the OneNote document, sorry? You have your computer. Do you have OneNote open? Okay. Thank you. Let's see what happens if I plug this in. This one has HDMI. And yeah, okay, I was probably putting it out early. I'll wash my hands so I don't make your computer dirty. Yay. All right, that's super helpful. Thanks, Marie. All right. So in spherical harmonics, the picture that you usually see is this one here, and that's the picture I used in my sketch over there. There are real formulations of spherical harmonics. There are complex formulations, and these are the ones that are usually drawn in quantum chemistry. These are the ones you might have seen in school. And the picture I much prefer actually is this one, because it highlights that here we describe angular distributions on a sphere. And this is now not a false color map, or, well, it is, but this describes complex numbers. So as we go around, let's say, the equator here, what we have is, as we go around the equator, there is a complex exponential. Yeah, we have cosine times I times the sine, and so these complex harmonics, they have unit magnitude here as we go around the equator. It's just the phase that changes. And, well, this would be a scalar. This would be our L equals 1 type. This is our L equals 2 type. And you see these nice zonal patterns. So here we have 0 nodal planes for our phase. Here we have 1 nodal plane, which is oriented like so and like so. Okay, the nodal planes are, you can think of them as here where we see these white stripes. Yeah, so 0 nodal planes, 1 nodal plane, 2 nodal planes, 3 nodal planes, and so on. And the reason we have all this complication in 3 dimensions relative to 2 is because in 2 dimensions, 2 rotations commute. So if you do first the other one and then the other one, or vice versa, it doesn't matter. So it's a commutative group or an abelian group. And in 3 dimensions, unfortunately, the rotations do not commute. It's a non-commutative group, and this is why everything becomes a lot more complicated. All right. Now here is a picture of the of Earth's gravitational field, and what I want to highlight here in this picture is that using spherical harmonics, which is what was used here, I can approximate any square integrable function on the sphere. And if I use low angular momenta or low frequency, like low frequency in a Fourier representation, I get a very smooth approximation. And as I use higher and higher angular momenta, I get an ever sharper approximation to the function. This is a point on the sphere, a single point on the sphere. We can also think of it as a function. No, it's just a Dirac distribution. So we have a 1 here, and everywhere else on the sphere we have 0. And shown here is what this single point on the sphere, if we expand it in spherical harmonics, and here they are shown, and these are the coefficients that we are using. If we multiply these coefficients with the angular momenta, or with the spherical harmonics, then this is the approximation to our Dirac distribution which we get. And if I were to continue here, so this was L equals 1, L equals 2, if we were to continue this with L equals 3, 4, 5, we would get an ever sharper approximation to the original vector. And what you see here is just this rotation behavior. So as I rotate, I can multiply with these Wigner-D matrices, and the important thing is that a rotation in spherical harmonics does not mix. So a pure rotation does not mix different frequencies. So rotating these will only lead to a different linear combination of these. So if I rotate a function composed of spherical harmonics, a rotation will mix the terms or the basis functions corresponding to a given angular momentum, but it will not transfer energy between different types. This is why we have this block diagonal structure. If, however, we now take the product of two such tensorial entities, you know, if you take a product of a sine with a sine, we get a function that has higher frequency content. Yeah? This is why always when we write this tensor product, why we then get out types that go up to k plus L. All right, so these are pretty pictures for spherical harmonics, and a comment on, you know, this is now the proper way to do things, to make the architecture equivariant, but you could also just, you know, present the same training data. Let's say if we predict energies, you could just predict the same molecule rotated and ask the network to produce the same energy. Or if you predict dipole moments, you could put in the molecule and the dipole moment in your training data, and then the rotated molecule and the rotated dipole moment. So this would be the data augmentation approach. And here is a recent paper by Johann Bremer, who was a math student in Heidelberg, and colleagues. And they point out that equivariant networks are more data efficient and more compute efficient. Yeah, so you see the loss here of the equivariant architecture is lower than the one you get when you do data augmentation. But the plot here on the left-hand side terminates at this really interesting point. But luckily you have Peter, and this is now a plot from Peter's paper. So this is Peter and Gerrit who did that work. They ran a similar experiment, but they continue beyond this point. And lo and behold, at some point, data augmentation actually is better in a really low training data regime. And we are still trying to figure out why. And yes, there's a question.
What's the baseline in the picture above?
What is the baseline in the picture above? I think that's with no data augmentation, but just, you know, having more and more training data. And this picture by Peter here, it does something else which is interesting, namely what I showed here, the equivariant point convolution. That's the most typical way of achieving equivariance, but it's not the only way. Another way is to use so-called local canonicalization, where you use local coordinate systems to describe what's happening locally. But if you do not inform these local coordinate systems about their relative orientation, you cannot pass tensorial messages. And Peter and Gerrit showed how to do the same with tensorial messages. And the nice thing here is that you can take any architecture and make that equivariant, and that gives you also the freedom to use you know, a richer set of non-linearities than just the gated one. There's a question. So the question was again about the baseline. So first of all, I don't know for sure. Yeah? Secondly, I think you know, this here training data set size, some of these training data sets are huge. And I think it really, and here I think they modeled a physical problem, whatever, ping pong balls gravitating around each other or something. And here, I think for the baseline, I think they used no data augmentation at all. Okay, all right. Good question, but I think I need to conclude because some of you need to go on to the next lecture. So, what's the summary of the day? The summary is that that there are different ways of achieving rotation equivariance. One is by data augmentation, one is by local canonicalization, and that's the most frequently used one in the literature, is in terms of equivariant point convolutions. Taken together, they are hugely boosting the development of this field of making reasonable predictions on highly non-trivial systems from molecular physics. And if you want to read about this, in my motivation today, I have followed this paper by Fabian Fuchs. If you want a high-level overview that discusses the relation of the Cartesian tensors that Peter talked about last time and spherical tensors that we talked about today, you can read a chapter in this high-level paper here. And if you want to get different perspectives, so from representation theory, from steerable filters, from the equivariance constraint, if you want to read different perspectives on the same problem, I recommend chapter 2 in this paper, which has 250 pages or so, and which has done a remarkable job of, this is a very diverse group of authors. And given that it's such a diverse group, they've done a remarkable job of, really bringing this into a single paper here and not just, a random collection of material. If you want to take the real deep dive, there's a whole series of lectures by Eric Beckers, who does in one semester what we scratched last time and this time. Very good. And I'm looking forward to telling you what can be done with all of this in the field of molecular physics and quantum chemistry on Thursday. Have a good time.